Okay, so we're continuing with our modeling, and we finished off with the tank mixing problem, and I'd like to continue now with some money problems. Money. And so we're thinking about interest rates, maybe a savings account, or maybe, sorry about the squeaky chair, talking about like a mortgage maybe. Um, and so let's think about this in terms of like a savings account first. And instead of coming up with the model itself, some people aren't sure where the model comes from. So let's think about how the money thing works. So suppose we start with like S sub zero um, amount of money with interest rate R, and that's annual interest rate, compounded annually. Eh. Okay, so that means that at year one, then we're going to have some interest rate coming, interest money coming. So the amount of money that we'll have will be your initial interest plus the interest rate times your initial amount, right? And so S1 you could write as S sub 0 times 1 plus R. Good. How about at the end of year two? At the end of year two, you're going to have S1 plus R times S1, right? Which would be S1 times 1 plus R. But then S1 itself is equal to this, so you have S0 times 1 plus R squared. And so you see where the compounding is coming from, and so you can probably guess, right? Oops. That S3, at the money at time 3 is going to be the initial amount times 1 plus R cubed, and so on. And so after n years, say, you could say 1 plus R to the n. Good. All right. So now the question is, what happens if you compound the interest more often than that? So if we change the model, or change the interest to R for annual interest rate, but then we compound the interest, compounded m times a year, how is that going to change our model? Well, um, for t years, or after n, maybe we'll say n years, after n years, we'll have S sub n is equal to S sub 0 times, now you're going to have a 1 plus, but the interest rate's not the same interest rate, right? How's the interest rate changing? If you're doing it like 4 times a year, then the interest rate that you're using is cut by 4, right? So it would actually be R over 4. And so the interest rate that you're now using is R over M, but then you're compounding it M times N times, right? And so now the question is, what happens as we can compound the interest? What happens as we compound more and more often? Well, you might recognize that as saying we're going to take the limit. Yay! What happens in the limit as m goes to infinity of 1 plus R over m to the m times n power? You know what? Let me keep that. Let me change that. Instead of n, let me change that to a generic time t. Okay? So that's instead of just having it at one specific year, and t is in years. T in years. All right. How am I going to take that limit? Oh no. Well, is this valid? This reasoning? As m goes to infinity, r over m goes to 0, and so therefore this goes to 1, and 1 to any power is equal to 1, and so this is equal to 1. No, that's not right. That's because as this term is going to 0, you're actually compounding it even more and more often. So the amount that you get actually depends both on how fast this is going to 0 versus how fast this is going to infinity. So they kind of balance out in this problem. And as it turns out, this is equal to e to the RT, where e is our ever popular 2.7128 ... Could you prove that? Sure you could. The proof involves L'Hopital's rule. And it's actually not too bad, but there is some algebra involved. So you might take a look at using L'Hopital for this. By the way, what we're doing is we're taking the limit of something to a power. Do you remember how to do that with L'Hopital? I'll just leave that as a hint. So if you're a math major, especially a senior math major, you might take a look at that. Okay. But for us, let's go ahead and just assume that for continuous compounding, we end up with the exponential function. And by the way, while I'm at this, why does the number e show up in nature so often? Well, the growth of a tree is actually very similar to the growth of money as compound interest, right? So what you're doing is you're growing at a certain, you've got some kind of percentage that you're increasing every year, right? And so the 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 way you would see how tall the tree is, right, or what the growth rate is very similar to what we've just done here. And so E always shows up in nature for like growth constants, and it's because it's very similar to the way interest rate works. Okay, I didn't want to get too far afield there. Now I know that my solution, the amount of money at time t I get is going to be the initial amount times e to the RT. What does that look like? That looks like the solution to our initial exponential growth of our population. That's true. That is right. Okay, so we can actually use the population model for money as well as other things. So let's go ahead and write down what our model is. Model for money. Model. Getting excited. It's going to be ds over dt is equal to, what's coming in is the interest rate times our amount, right? And then I'm going to say plus k if this is a savings account, and so k is going to be, k is the amount per year that we're paying in. So you have to keep your time units the same. Good. And so if this is a savings account, right, a savings account, this would be a plus sign. But if it were a mortgage and you're trying to figure out the amount you owe, amount of money you owe, you might say that it's ds over dt equals rs. That's growing the amount of money you owe, but then you're paying a certain amount, so that would be a minus k. Good. And then finally, how would you solve each of those problems? The solution to both is going to be s of t equals, we already know how to solve these, that's ce to the rt minus what? minus k over r. Very good. Now, I should say s of 0 equals s sub 0, so could we solve for c? So then s sub 0 would be c minus k over r, or c would be s0 plus k over r. Okay, and so then our s of t, the amount of money we have is, you could write it as s0 plus k over r times e to the rt minus k over r, or you could write this as s0 e to the rt, and then you have the k over r over here plus k over r, k over r, and then you have an e to the rt minus 1. So that's another way to write it, if you like. Good. Okay. Let's see, I'm at the 11-minute mark, so I think I'm going to have to cut my money example into a couple pieces, and so we'll take a look at another example in just a minute.